VC dimensions. VC. V stands for the mathematicians Vapnik, and C, which it stands for the mathematicians Chervonenkis. Okay, these are the two guys, two mathematicians in early 90s. They have discovered this technique to find the how much powerful of his such kind of class of models is. Okay, and if you remember the Vipnik, these mathematicians are already invented the beautiful machine learning theoretical concept like SVM. Okay, already we have learned this concept. This guys means Vipnik. He is already invented these SVM support vector machines. We have already learned this concept. Now, why we need to learn this VC dimension concept? Why this is important? So to measure the how much powerful of a class of models is, to measure it, actually these concepts theoretically give some idea. Okay, so how much powerful is a class of model is? To measure these things we need to. So this class of models already we have covered. There are class of models. You can think linear models, or you can think this is a RBF SVM, radial basis functions SVM, or you can think this is a boosting algorithm like that. Okay, boosting algorithm means decision trees, group of decision trees, random forest. It means there are various boosting algorithms. And when we learn to discuss the neural network, then it is also a class of models. Okay, there are various kind of linear networks, a neural network. We will see these things in details. But these kind of group of models there exists. Also, there have various, but these are the popular scenes in more general we have used. Okay, but the question is to measure all the class of models. If we somehow got some numerical quantity, if we somehow got some numerical quantity, then it will be give some more realistic intuitions to realistic decisions how much these models is. Okay, already in fact, if you see these things in practical expected, so already we have seen some accuracy metrics like this kind of performance metrics we have seen to find the measures. But this is the another kind of concept, means this you can think like a theoretical concept. This one is, so you can think this is kind of theoretical perspectives. In theoretical perspectives, okay, means this powerful to measure this performance of the powerfuls. So you can think like a theoretical part of the machine learning means that we can use the accuracy matrix, various kind of matrix formula we have seen. This is the practical scenarios, but in theoretical concept these VC dimensionally useful. So these things are actually used theoretical part of the machine learning. Okay, so yeah, you can think like a theoretical part of machine learning means I'm talking about the statistical machine learning, or you can think this like is a computational learning machine learning theory. Okay, these kind of are part of these techniques are part of the theoretical machine learning part. Okay, you can think like a computational learning theory. Okay, these are the in I'm not going to discuss everything, but these things I'm going to the intuitions. What is actually this VC dimensions gives the idea to measure the performance of some class of models. The intuitions I'm going to give. I am not going to give you the every mathematical details. If you are interested, then you can learn yourselves. Okay. Now first just try to understand the intuitions behind it, why these things are actually needful. So, so in practical scenario, we have seen to measure these models. In practically, we have seen in practical, we have practically using the data sets. Using the data sets, we can find some matrices like AUC matrix, XR square matrix, like that. Various technique we know. Okay, we know. But this is the concept of the VC dimension is the theoretical part. Now let's try to understand through an example how these things are actually, what is this meaning of these VC dimensions? What is this? After understanding this part, then I am coming to the definitions of it. So let's try to understand these things through the linear model. I think it will be better for us if we use the linear model to understand. So it will be more visualizable, easily visualizable, and it easily you can understand these things. Then we can easily extend this concept for the rest of the models. So for the linear models, if you linearly think these things to separate to different type of points, we needed a what? To separate it, we needed the line in 2D. If you think like a 3D system, then we need a plane. If you think like a multidimensional means ND systems, we need a hyperplane. We need a hyperplanes. So these things in machine learning, these things are called the decision surface. These things called the decision surface. So here or another language, these things you can think like a shutter. Means that are the that things are helps us to separate it to different kind of things. So you can think these things like a shutter. It is also a most popular word in machine learning, using this word shutter. Okay, in shutter means we want to separate it from this one. I mean the two different things we want to separate it. Okay, so first let's try to understand through these 2 points. Suppose let's in a plane we have in some systems we have only 2 points. Then is it possible to separate it? Suppose let's we have only plus 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 plus. If it is if there have no negative points, only plus plus, then it is obviously it is possible. If only we have two negative points, then it is obvious it is separatable. Suppose let's if you have like that plus minus or minus plus or like this one, this type of plus minus, it is obvious any kind of combinations you can take, it is always possible to separate these two lines like that. If it is here plus minus, then yes, it is also possible. So any combinations you can take for 2 points, it is always possible to separate these two data points. Okay, now let's see it through the 3 points. If you take the 3 points, let's see it. Suppose let's we have 2 plus 1 minus. Yes, it is possible. If it is plus plus minus, yes, it is possible. If this is minus minus plus, yes, it is possible. or another link thing. Anyhow, if they have all the plus, yes, it is also possible. All the minus, yes, it is also possible. Like any combinations you can take, any combinations, it is always possible to find a plane or high plane or a line or a hyperplane to separate these points. For 3 points, it's also okay. Now let's see through the 4 points. If we consider the 4 points, then what happens in such scenarios? So suppose if this type of points we have, then yes, it is possible to separate it. If this type of points we have, yes, this is also possible, but the problem occurs here. If we have this type of problems, plus minus minus plus, if this type of problems have, then it is not possible to separate these points through a single plane or line or hyperplane. Okay, just see it. It may needed this type of planes. If you draw, it is also impossible. If you draw this line, it is also impossible. So any single line cannot separate this group of. So that's the problem. That's the question occurs here. So here the question, that's problem. Here we have to face. I am not able to settle. I am not able to settle 4 points. Okay, it is totally impossible for a single line. Using single line, we cannot separate it. Okay, so now the definitions here comes into the pictures of the VC dimensions. So the definitions of the it, so there exist at least one configurations of 4 points such that these 4 points cannot be settled. Okay, simple using, just write this problem in a more literal way. So there exist at least one configuration. Configuration means I'm talking about this is one configuration, this is one configuration, this is one, this is one, this is one. Just combinations of. This is called one configuration. So there exists at least one configuration. One configurations of 4 points such that these 4 points cannot be settled. Cannot be settled. This is the main problem. So based on this problem, the VC means Vapnik and Chervonenkis, these two mathematicians have developed this formula. So the formula of this is the VC dimension for this means these models that I have taken here, it is a linear model. The VC dimension of a linear model this formula is 3. Why 3? So 3 because the numerator here, so the 3 because it is the maximum number of points that can be separated by a linear models for all possible configurations. Just see it. When we have taken the 4 points, then we got in one configuration that cannot be separated by using the single line or single setter. So in general we call it setter, but here in the linear model we call it a line or plane or hyperplane like that. So just see it. Or it is totally impossible for 4 points, but it is possible. If you take any configurations for 3 points, it is always possible to find a setter that may separate it this point. So this is the now coming to the pictures. So the definitions now, it will be the maximum number of points, the maximum number of points that can be settled by a linear model for all possible configurations. This is the simple. So the concept of is the BC dimensional is the maximum number of points that can be settled by a single by a single settled by a linear model for all possible configurations. That's the simple concept. Since we have taken here linear models, if we taken here the different kind of models, so different shape of setters there will be. So simple. This is the main concept. So now it is extendable for different person to persons. Okay. I think from these discussions, you got the point, idea, how this VC dimensional is actually look like. Now let's see it, how these things, how this concept of the VC dimensionals are actually useful to find the how much powerful of a group of models is. Okay, let's see it. I think from these discussions, you will understand the VC dimensions of the linear models. Now let's try to understand the VC dimension of boosting classifier models. So what is this? So let's understand. I am not going to discuss the mathematics details, mathematics part. Just I am to going to intuitions. How's this actually work? So let's try to understand it. So now the VC dimensions of a boosting classifier. Okay, let's see. Suppose let we have a base class of B simple classifier. Means boosting means there have some simple classifiers, and on this using these classifiers, using some combinations of these classifiers, we have built the boosting classifier. That's the job we are doing in boosting technique. So let suppose suppose we have a base class of B simple classifier. Base class B of simple classifier. Okay, and to whose dimensions? VC dimensions for each PC, for each base classifiers, for base classes. We have a B simple classifier B for each this kind of these B's whose VC dimensions is let D. Let its VC dimension each D. Okay, let now the VC dimensions of the set of such classifiers. Suppose let the T classifiers we have taken from these classes. This is the simple. B is the simple classifiers. Okay. Now from these classifiers we have to make some group of classifiers. This is the B of simple classifiers. Okay. This number of B means the you can think this is like a number of simple classifier. Okay, so this is the simple number of simple classifiers. So from these classifiers, let we choose T classifiers. T classifiers like it may be H1, H2 like that, HT. It's all are belongs to. We have chosen randomly. We have chosen such kind of T classifiers from this simple. Okay, we have chosen, and let its weights vectors be belongs to each weight vectors and its weight vectors for h1, let its weight vector h1 w1, for this its weight vector w2, it's respectively. Let it belongs to the the set rt, t dimension. Okay, since you have t class here, classifiers we have taken, so its dimensions also belong to class t. So why these things happen, I'm going to discuss this. So if these things happens, so in such scenarios, the VC dimensionals, the set of such classifiers, this is the set of such classifiers. Okay, so VC dimension of the set of such classifiers is now the this is the VC dimensions of the single classifiers. So B number of the classifiers that we have taken, simple classifiers. If we choose this P number of classifiers from this base classifier, then its VC dimension will be, so VC dimensions of the set of such classifier. Such classifiers means I'm talking about here the for all selections of T classifiers from B, and its corresponding weights is belongs to RT. Okay, that's I'm talking about. So for all selections of T from B. Okay, means I'm talking taking here T. It may be 2 or 3, 5, 9, 10, like that. Like this kind of selections, man, that may I take. Total means we have simple classifier. So it will be think like suppose we have a logistic regressions, linear regressions, decision trees, SVM, naive base, like that. We have suppose like that B number of simple classifiers, and from here we will take such kind of T classifiers. Okay, these T classifiers. So T means I'm talking about T. T means number of subsets from this B we have considered. And H models, H based classifiers weight is if this, then this set of such kind of classifiers, its VC dimensions will be using this formula we will find. Okay, I think you will got the point what I am going to say. Okay, its VC dimension will be simple E into D plus 1 into 3 log of E into D plus 1. It will be better if I use here this curly E plus 2. So this is the simple formula. Here we know what is the D. D is the simple, the VC dimension of the H simple classifiers, and we know what is the T, how much models we have chosen to our sets, in our sets. So this is the simple formula to find the, so to find the simple means it's not always equal, it's approximately equals to. This is the simple using this concept. Okay, so this is the simple formula. I'm not going to discuss how this formula has come. If you're interested, just search it on Google. You can easily find it. There are various books and literatures available already. Just using this formula. Okay. So so the using this BC dimensional concept, this theoretical concept, now we can conclude that if a BC dimension of such models, let M1 is greater than is equals to BC dimensions of such models, let M2. If this happens, then we can conclude that the model 1 is better than model. We can conclude, not practically, theoretically. Theoretically. So there are totally huge differences, theoretical and practical, between theoretical and practical. So let's see. If you find the BC dimensions of the RBM SBM, if you calculate it, the BC dimensions of the RBF SBM, if you calculate it, you got it infinity value. Its value is infinity. Okay. So it's BC dimensions. That means what? It means theoretically it's overall good. It's BC dimensions infinity is in overall good. It is so, but it does not imply. So it implies theoretically, theoretically it is always better since its BC dimensional is infinity. But in practically, in practically, it does not imply that RBM SBM is the best in practice. Okay, so in practically, it does not imply, that RBM SBM is the best in practice. As always, that's the thing. As always, it's not good. Sometimes it's good, but in practical, if you think like, it's not always. So the theoretical concepts and the practical concepts are totally different. So I think from these discussions, you got the idea how these things are actually usables in a real world. Okay, so there have lots of theory in the BC dimensions. I'm not going to discuss. If you are going to research on it with the theoretical perspective of the machine learning, then there have a whole course. The PhD guys, those who are going to doing their PhD, they have applied to justify this concept of BC dimensions to to justify their model how much accurate it is. So this is the one kind of theoretical concept. I'm not going to discuss. If you are interested, if you're going to build your or further academic career after masters, after master, if you're going to doing your PhD on it, then you are learn it. Then you will going to learn it. So it's okay. But in applicable point of view, it's not so much important. So I am going to just giving you some the flavor of it, how these BC dimensions are actually workables on real world, how these things are actually usables for the theoretical models, how to justify the theoretical model, how much good is these things are actually used. So there have lots of means huge mathematics you have to know to understand this concept. Okay, So this is the simple VC dimensional. This is the main primary concept of it. VC dimensional is the simple concept is the maximum number of points that can be settled by a simple models that are all possible, that are used by using all possible configurations. This is the simple geometrical. But behind this geometrical concept, there have lots of mathematics. You have to know it. If you are going to build your academic area by using the machine learning theoretical part, then you have to learn. Don't there have no compromise. But in practical scenario, it's not so much important. Okay. So I think from the discussions you got some flavor of it. How much or what is the VC dimensional? If you have any problem, request you please comment below. I will try to help. I will try to help you at as much as I can.